All right, welcome back. Have you ever wondered how you can ask a gigantic database a super specific question and get the perfect answer back in like seconds? Well, it's not magic, it's actually logic. And today we're going to pull back the curtain on something called relational algebra. Think of it as the hidden language, the powerful grammar that lets us talk to data and get exactly what we need. So let's dive in. So picture this. You've got these mountains of data, right? Massive tables full of information. But you don't want all of it. You just want one specific thing. How do you ask for it? I mean, how do you phrase that question perfectly? Well, that is the exact problem relational algebra was built to solve. It gives us a formal, almost mathematical way to construct the perfect question every single time. So, here's how we're going to break it all down. First, we'll cover the basic language of databases. Then, we'll get into the fun stuff, filtering rows with selection and picking columns with projection. After that, we'll see how to combine data from different tables, start thinking in data sets, and finally, we'll connect all this theory to how it's actually used in practice with SQL. All right, let's start at the beginning. To really get a handle on how to query a database, you first have to understand the language it thinks in, the core rules that make everything else even possible. And this right here is the absolute key idea. You gotta get this. Think of relational algebra like a machine. A table goes in one end, and a brand new table always comes out the other. It's a completely closed loop. Every single operation you do just creates a new table from the old one. And this is what makes the whole system so incredibly elegant. You do an operation on a table, you get a new table back, right? And that new table can immediately be used in the next operation. It's kind of like having a set of Lego bricks for your data. You can just keep snapping new operations on top of each other to build whatever you want. Okay, so our first tool is all about filtering. I want you to imagine you have this giant spreadsheet in front of you. The selection operator, well, it's like taking a ruler and just slicing out the exact rows you're interested in. It's a perfect horizontal slice of your data. Now, the formal name for this is the selection operator, and you'll see it represented by the Greek letter sigma. Don't let the symbol scare you. This is simply our go-to tool for setting a condition. Think of it like a filter in Excel to pull out only the rows that match exactly what we're looking for. So, for example, let's say we have a books table, and we only want to see the ones about databases. We'd write it just like this. We use sigma, we state our condition, subject equals database, and then we just tell it which table to look in. See? Simple, but incredibly powerful. So, a few key things to remember here. You can build some really complex filters using things like and, or, and not. And what's really cool is that it's commutative, which is just a fancy way of saying the order doesn't matter. Filtering for price and then subject is the exact same as filtering for subject and then price. And notice, the number of columns never ever changes. You just end up with fewer rows than you started with. Okay, so if selection was our horizontal slice, our next tool, projection, is the complete opposite. This time, we're taking a vertical dice to our data, letting us chop out just the columns we want to see. This one is called the projection operator, and it's represented by the Greek letter pi. So after we've already selected the rows we want, projection lets us decide which pieces of information from those rows are actually important for our final result. All right, let's look at a quick, practical example. Here's our source table, a simple list of students with their ID, name, subject, and age. Now, let's say we don't care about their ID or what subject they're taking. We just want a clean list of names and ages. So we use the projection operator, pi, and we just list the columns we want to keep, name and age. That's it. And boom, here's our result. Just like that, we've created a brand new table that contains only the columns we asked for. It's a perfect vertical partition of our original data. And really, this is the fundamental difference you have to remember. Selection slices horizontally to filter your rows. Projection dices vertically to choose your columns. And in the real world, you're pretty much always using them together to pinpoint the exact piece of data you need. So up to this point, we've only been working with one table at a time. But honestly, the real power of databases comes from connecting information across multiple tables. So let's see how that works. So how do we combine tables? Well, the first way is kind of the brute force method. It's called the Cartesian product. It just mashes every single row from the first table with every single row from the second one. As you can imagine, it usually creates a huge, messy result. The smarter way, the way we almost always do it, is the join. A join is really just that messy Cartesian product, but with a selection filter applied right on top of it, merging only the rows that actually relate to each other. Like where a user ID in one table matches the user ID in another. This is the real workhorse of relational databases. Okay, we can also shift our thinking a little bit and start treating our tables not just as tables, but as mathematical sets. And when we do that, it opens up a whole new toolbox of really powerful intuitive operators. But there's one critical rule you have to follow first. For these set operators to work, the tables have to be what's called union compatible. It sounds complicated, but all it means is they have to have the same number of columns, and those columns have to hold similar types of data. You can't, for example, merge a column of names with a column of dates. It just doesn't make sense. First up, we have union. The easiest way to think of this is as the OR for tables. It gives you a single new table with every row that's in table R or table S, and as a bonus, it automatically gets rid of any duplicates for you. Next is intersection, which, you guessed it, is basically the AND for tables. Your result is a table that contains only the rows that exist in both table R and table S. It's perfect for finding the exact overlap between two different data sets. And finally, there's difference. This is our NOT operator. If you do R minus S, you get only the rows that are in table R, but not in table S. It's how you find out what's unique to that first data set. Okay, I know this has all been a little bit theoretical, right? Lots of Greek letters and abstract concepts, but here's the payoff. This abstract algebra we've been talking about, it is the direct intellectual foundation for SQL, which is by far the most common database language in the entire world. So let's see exactly how this translates. Our projection query from before, TIE, name, age of student, well, it looks almost identical to the SQL query select, name, age from student, doesn't it? But there's one super important difference. Relational algebra, in its pure theoretical form, automatically removes duplicate rows. In SQL, though, duplicates are kept by default. You actually have to tell it to remove them by adding the keyword distinct. It's a small detail, but it tells you a lot about the theory versus the real-world practice. So you see, relational algebra isn't just some dusty academic theory. It's the hidden logic, it's the why, behind every single SQL query you'll ever write. And understanding it doesn't just make you a better programmer, it makes you a clearer, more powerful thinker when it comes to data. So now that you know the grammar, what new questions are you going to ask?